Hi there, and welcome to our technical tour, which is all about grimsel, the car that has just broken the world record for fastest electric acceleration. During this tour, we would like to give you a short insight about the ideas and the thoughts that went into this car. Also, we'd like to highlight some of the features and the concepts that make grimsel not just a great sprinter, but actually one of the most successful cars to ever compete in a so-called Formula Student competition. But enough chit-chat, let's have a look at the car. Grimsel, just like all of our other cars, is named traditionally after a Swiss Alpine pass. And the first thing I want to point out about this car is that, with the exception of just a very few, almost all the parts are self-developed by the team itself. If we have a look at all those parts in a disassembled state, those exceptions which are bought or sponsored are the tires, the cells for the accumulator, the motor controllers, and a few smaller electronic components such as cables, buttons, LEDs or sensors. It sounds like a lot of effort to develop all these parts, and it truly is. But by designing each part for its specific purpose and the occurring load, we're able to maximize the whole performance of the complete car. Now, the chassis, for instance, is a great example of why specific design has great opportunities for us. The chassis of grimsel is a so-called monocoque, and in contrary to a normal space frame where the loads are transferred through single struts that are welded or screwed together into a truss-like structure, a monocoque has a single load-bearing shell. It actually comes out of the mold as a single part. Now, this has a lot of advantages for us in combining the shape and the structural purposes. In case of grimsel, the shell that makes up the monocoque is made out of a sandwich structure that consists of a carbon fiber reinforced plastic on the outside layer and a core, the so-called core in the middle, that is made out of aluminum honeycomb. Now, this concept is extremely versatile as it can be adjusted to all the different load cases individually in each area of the car. We can do this by adjusting the height of the core or by adjusting the amount of layers and the type of carbon fiber that we use on the outside. By doing this and optimizing the monocoque like that, we can build extremely light structures. Grimsel chassis weighs only 14 kilograms. That's light enough that a single person could lift it up and just walk away with it. Alright, I've been telling you quite some details about the structural parts of the car so far, and now my colleague Yves will join me and he'll tell you some more about the performance and the design of the car.
To get the load from the chassis to the tire, we need a suspension. The design of the suspension is a very complex trade-off between different targets for the vehicle's performance. Usually we have to fix this trade-off before the race, but in grimsel we bring a novel technique to solve this problem. Grimsel is the first race car worldwide known to us to implement adaptive damping. This means that the damping constant can be adjusted to the current driving situation. This is enabled by a magnetorheological fluid this in the damper. So these fluids have the characteristic that they change their viscosity if a certain magnetic flux is applied. The magnetic flux is changed by these cables due to a current flowing through the damper. So, for example, in a cornering situation, we need a high mechanical grip. So we use a soft damping, and in a transient situation we want to have a fast responding car, so we use hard damping setup. So that now we have a chassis and tires attached to it, we need something to accelerate the whole, a drivetrain. I will show it to you. Here is where grimsel has some very innovative features. We use a four-wheel drive car with wheel hub motors, meaning that at each of the wheel hubs we have a motor with 50 horsepower and weighing 3.4 kilograms. So the power to weight ratio of our motors is much higher than those of the other known motors. Even the motors from the Formula E don't have power-to-weight ratio as high as ours. The motors spin up to 19,200 RPMs, so we need a reduction gearbox. Because we can apply the maximum torque to about half of the maximum speed, we don't need any gears to shift. We use a fixed transmission gearbox. This allows us to build a planetary gearbox, which is very lightweight and compact. So, like you can see, we built the whole gearbox inside of the wheel hub. The concept of four-driven wheels gives us a lot of opportunities for the control systems. So, for example, Grimsel uses a wheel individual traction control system, meaning that each wheel has optimal grip in every driving situation. Additionally, we use a torque vectoring system. This means that we distribute the driver requested torque to each of the wheels individually in an optimal manner for the given driving situation. So, for an example, if we find us in a right corner, then the left wheels give a higher torque than the right wheels, leading to a steering moment that supports the usual steering that we have by giving an angle to the wheel. With the traction control and the torque vectoring, we make sure to get the full potential out of the car's performance by increasing its stability and agility. Now, to implement such complex control algorithms, we need a board computer, the so-called vehicle control unit. It samples all the information from the various sensors that we have on board, for example, the wheel speed, the accumulator cell temperatures, the speed of the chassis, the accelerations on the chassis, and the driver inputs. A 200 horsepower race car needs a lot of energy, so Lucien is now going to explain you how the accumulator works.
What you can see here is the inside of our accumulator container. It contains 448 of these lithium polymer cells that add up to a nominal voltage of 414 volts. The cells are bought, but the structural and electrical integration is also self-developed, as well as the battery management system. It allows us to control and monitor the temperatures and the cell voltages at all times during a race. We also have an air cooling system that cools the accumulator container down in case of high power demands. In total, the accumulator container has an energy capacity of about 6 kilowatt hours. This allows us to drive 22 kilometers in race mode.
The main goal during the design of a race car is to increase its longitudinal and lateral acceleration. But these accelerations are restricted by the force the tire can bring to the track. To increase this force, we can use aerodynamics, which press the tire with a higher force to the ground, and therefore increasing the accelerations we can achieve. On Grimsel, we use a front wing, an under tray, and a rear wing. With this whole aerodynamic setup, we can increase the performance of Grimsel remarkably. So, for example, at 110 km per hour, the aerodynamics produce a downforce such high that we could theoretically drive at the ceiling. Now, to increase the efficiency of the car, we use a drag reduction system. So for that we use a motor in this box that enables the driver to tilt the last flap of the rear wing and therefore reduce the aerodynamic drag.
We've now gone almost through the entire race car and how we design it, but we've missed out on one very important aspect, and that is the interface between the driver and the car itself, namely the steering wheel, the pedals and the seat. So let me start with the seat. In order to make our drivers feel as comfortable as possible, we have actually molded our seat from a living person's butt. Feels good, doesn't it? So let's have a look at the pedals. Since the seat is fixed in place, the pedals are individually adjustable for the position in order to seat larger and smaller drivers. And as we have no clutch, there are only two pedals, one for throttling and one for braking. The brake pedal is preloaded by a gas spring and has an electronical sensor implemented. Thus, we are able to use only our electric motors for braking until the driver exceeds a certain force, and that's when the mechanical brakes kick in. By decoupling electrical and mechanical braking in such a way, we are able to recuperate over 30% of the energy in the accumulator and reuse it in any time during the race. The last part I'd like to show you is the steering wheel. It is also made out of carbon fiber, and it is shaped in a way such that the driver has a comfortable grip and a direct steering experience. It also features a few buttons with which the driver can actuate the radio or change parameters of the car while he's driving. In the back there are flappy pedals with which the driver can actuate the drag reduction system. Here you go. Well, that's it. That's the end of our tour. I hope you've learned something new and enjoyed our explanations. In case you'd like to find out more about our team or the Formula Student in general, please feel free to have a look at our other video. Thanks for watching.